In this work, it will be shown some information about the compound interest, exponential growth, radioactive concepts and its formulas, the half-life of radioactive element californium-234, and how to obtain it. And also a math problem will be solved following the steps required to find the answer to each question. It will contain a flowchart for a better understanding of how the problem was solved. By the other hand, there are 7 questions that will help the team in order to have a good comprehension about the theme. Without further ado, the questions are presented first as a way to introduce people to the subject it is going to be treated. Investigate the concept of compound interest.
Is the interest calculated in the initial capital and also the accumulated interest of previous periods of a deposit or loan? Compound interest is known as the interest on interest, and its main purpose is to make a deposit or loan grow at a faster rate than sample interest, which is the interest calculated only the main amount.
Write down the formula for interest compounded n times per year and explain each variable of the formula.
Based on what Stewart, Redlin, and Watson said, it is A of t equal to b per 1 plus r over n elevated to the power of nt, where A of t is equal to the amount after 2 years, b is the principal, then r is the interest, n is equal to the number of times the interest is compounded per year, and t is the number of years.
Write down the formula for interest compounded continuously and explain each variable of the formula.
Stewart, Redlin, and Watson said that the formula is A of t equals to b per e elevated to the power of rt, where A of t is equal to the amount after a time t, p is the principal, r is the annual interest rate per years, t is the number of time in years, and e is equal to the Euler's number.
Investigate the concept of exponential growth.
It's the development of an increasing fast rate in proportion to the increased total number or size. It happens when the growth rate of the value of a mathematical function is proportional to the function's current value. Compound interest is an example of exponential growth.
Write down the model of exponential growth in relative growth rate and explain each variable of the formula.
Stewart, Redlin, and Watson said that it is n of t is equal to no e raised to rt, where n of t is equal to the population at time t, and no is equal to initial size of the population. R is equal to the relative rate of growth expressed as a proportion of the population.
T is equal to time, and E is equal to Euler's number.
Investigate the concepts of radioactive decay and half-life.
Radioactive half-life for a given radioisotope is a measure of tendency of the nucleus to decay or disintegrate, and as such is based purely upon the probability. By the other hand, radioactive decay is a spontaneous breakdown of an atomic nucleus, resulting in the release of energy and matter from the nucleus.
Write down the formulas of radioactive decay model and the half-life formula, and explain each variable for both formulas.
Following Stewart, Redlin, and Watson information, the half-time formula is modeled by m of t is equal to mo 2 minus t over h, where h and t are measured in the same units, second, minutes, hour, dates, etc. M of t is the mass remaining at the time t, and mo is the initial mass. To express this model in the form m of t equal to mo e raised to the n, it is needed to find the relative decay rate, since h is the half-life it has.
Mt is equal to moe raised to the power minus rt model. Mo over 2 is equal to moe raised to the power minus rh. H is a half-life time. Then 1.5 is going to be equal to moe raised to the minus rh divided by mo. Then natural logarithm of 1.5 is equal to minus rh. Take natural logarithm of each side. Finally, isolate r. Then we have that r is going to be equal to the natural logarithm of 2 over h.
This equation helps find the rate r from the half-life h. Therefore, in the radioactive decay model, if mo is the initial mass of a radioactive substance with half-life h, then mass remaining at time t is modeled by the function m of t is equal to mo e raised to the minus rt, where r is equal to lateral logarithm of 2 over h, t is equal to time remaining, and e is equal to the Euler's number.
The objective of the questions answered before was to give the team a better comprehension in the problem's theme. Now, it is presented the problem with each of the answers. But before this, it is a flowchart based on how the team solved the problem.
To start, read the problem and questions, identify the given variables, solve the problems and questions that do not any other formula than the given one. In the half-life formula is not clear yet, our research can be done in order to understand what is solicited. Read the given equation.
To get the half-life, use the next formula. T is equal to natural logarithm of n minus natural logarithm of n0 over k, where n is equal to any mass quantity, n0 is the initial mass, k is the decay for which we multiply the time in the original formula.
Do that the both are looking for the half-life, it will be the same as queuing as numerator Ln to the 1/2. Solve the division. Read again the questions and answer so the information will not be misunderstood. Write down the answers for the remaining questions. End.
The problem is the following. Problem 8. The mass MT remaining after T days from a 40G sample of thorium-234 is given by MT equal to 40E raised to the power minus 0.0277 T. How much mass will be remaining after 30, 60, and 90 days? First, replace the quantity of days in the value of T. After this, multiply minus 0.0277 per T. Then, raise E to the product of the previous multiplication. Finally, multiply the previous product by 40 and you will get the results.
Find the half-life of thorium-234. Looking for the formula to get the half-life of any element, it was found that it is need to use a natural logarithm in order to get not just the half-life, but any amount of time needed to get an exact quantity of mass. And the formula says that T is equal to natural logarithm of n minus natural logarithm of NO over K.
Where K is the decay minus 0.0277 and NO is equal to the initial mass. So being the initial mass 40 grams and the mass that is want to get 20 grams, half of the original amount of grams, so it can be said that T is equal to natural logarithm of 1/2 over minus 0.0277 is equal to 25.02. Therefore, the half-life of this sample of thorium-234 is 25.02 days. Graph the model from the equation given, leaving T as a variable. Graph a new model from the same equation, but with a rate of decay of 4%. From the previous graphs answer, which of the two models from questions D and E is decaying faster? Why?
The second model, because the rate of decline is 4% and it's bigger in comparison of 2.77% of the other model, which means that the second is going to decay faster.
After solving all the points of this problem with help of some information about the radioactivity, the half-life of the radioactive elements, and some knowledge in math, all the answers to the questions that the problem gives were solved. In the first one, it was found that after 30 days we remain 17.42 grams approx of thorium-234. After 60 days we'll be remaining 7.6 grams approx of the same substance, and after 90 days 3.31 grams approx of it. In the second question was discovered that it will take 50 days to have remaining 10 grams of thorium-234. In the third was obtained that the half-life of this element is 25.02 days. This type of problem can be also used in real life to obtain the half-life of any other radioactive element. If there is a place where the radioactivity is too high, with this it can be determined in how much time this place will be habitable again. Moreover, it can be used to determine when it's safe to touch a sample of radioactivity material. It is safe when the radioactivity drops below the detection limits.
It's amazing to know that radioactive decay models is used to know the behavior of some elements of this type. This model uses probability. Another use is that with the half-life of some elements like carbon-14 helps to know an approximate age of some remains of bodies like dinosaurs.